I hope you guys are doing well. This is going to be my Lab 1 report. So the purpose of this lab is to compare the observed positions of a real object that's moving at constant velocity with the predicted positions generated by a computational model using close grip. So, and also we're going to be we're going to explore how this lab is going to relate to physics principles, particularly these two principles. So momentum principle / Newton's second law. These are basically the same thing, and I'm going to explain why. You have momentum equal to mass times velocity. So and then F net is equal to the derivative of this momentum. When you're calculating the derivative, you're going to get this, and then you can take out mass when mass is constant, and this is equal to acceleration. So that's how these two are basically the same thing, because Newton's second law is force is equal to mass times acceleration. In terms of this slab, since velocity is constant, that's going to make momentum constant, and the derivative of a constant is going to be 0. So F net is 0. Keep that in mind. All right, Newton's first law, we're going to be focusing on this object in motion. When an object is in motion, it's going to stay in motion unless acted on by an unbalanced force. But as we just said here, F net is 0. So there's going to be no forces acting on this object in motion. So it's going to have the same motion. It's going to have the same velocity. These are really important equations we're going to be using. The velocity update formula, which is from this. The position update formula, which is from this average velocity formula. So experiment. The purpose of this is, well, this is a tracker app right here. It's going to help extract positions versus time data. And some of this data is going to be used in the computational model. So yeah, first, this is the system. Our marker is going to be the system. The surroundings is going to be the table or other forces. But we're going to find out how these forces are pretty much negligible. I'm going to play my video. So yeah, started tracking data over here. And it doesn't matter if I started here or everywhere or just here, because velocity is constant. And my calibration stick is at 0.1 meters. All right, tracker data. So yeah, I said we're going to use some of this data for our computational model over here. We're using the velocity average formula right here. So we took 0.012875 meters minus 0 meters, these 2 points, over the change in time, which is 0.033 seconds because my video is in 30 FPS. So yeah, all of these are, basically the change in time for all of these is 0.033 seconds. We're going to get the average velocity, or well, velocity initial, which is going to be the same thing, to be 0.390 meters per second. Total time I took is 2.035 seconds, and I started at 1.468 seconds. So yeah, started at 1.468 seconds, ended at 2.035 seconds in the while loop. Mass, I'll get to that later. The ball position is going to be 0. We started at 0. Velocity, we calculated it to be 0.390 meters per second. So yeah, and our while loop is going to produce the calculations for our graphs. F net is the 0 vector because we have constant velocity. And since F net is a 0 vector, it doesn't matter what the mass is because 0, anything under 0 is just going to be 0. So this whole thing's 0. And we have velocity final is equal to velocity initial. And that basically defines constant velocity. And then this equation is going to help produce these graphs. We have position increasing at a constant rate, and then the derivative of position is velocity. So that's why velocity is at constant rate. That's why velocity is constant. And constant velocity proves that F net is 0. Yep, side-by-side comparison of the observed position and the predicted position. We have this, and it's on my data points. Error. So some errors, as we can see, they're not perfectly lined up, and that's because of the tracker measurement errors or the model assumptions, because I'll get to that later. So when clicking points in tracker, there's going to be a few misplacements by a few pixels that could lead to differences in extracted positions and changes in time. Also, maybe my calibration stick wasn't exactly lined up to the meter stick in the background. That could also lead to some errors. Model assumption. So we assume that F net is 0, but in the real world, there's going to be small forces acting on my system, which is the marker. So maybe, in my case, we see that the tracker data is over the computational data. So maybe there was some forces moving the system a little faster. All right, final questions. What if and what does this mean? What if I flip my axis so plus x and negative x were interchanged? What this is going to do is it's going to make your position versus time graph decrease at a constant rate. And that means that the velocity will be a constant negative value, but velocity is still constant, so F net is still 0. What does it mean for you to say how many pushes and pulls are being added together to give 0 net force? So what this means is identifying the individual forces acting on the object, like friction, air resistance, contact forces, that combine to produce the overall net force. And so, yeah, let's answer this part now. Is it possible? Is it possible for you to say how many pushes and pulls are being added together? In our case, we can't really tell from the video exactly which forces are present or how many there are, but we know that when they're all added together, their total is 0, which keeps the object moving at constant velocity. Yep. That's it. Thank you. Have a good day.